Hello, Calculus. Today we're going to be going over the antiderivative and the integral. And we begin this exercise, this class, with section 4.9. So this is where we're at. So let's make a definition to start off with. F is an antiderivative, big F that is an antiderivative of little f if the derivative of big F equals little f, and little f again is a function of x. Alright, so this is the definition of what an antiderivative is, right? It's the opposite of a derivative. And so the most general antiderivative is going to be this f plus some constant. And if you take the derivative of the whole thing right here, well, what are you going to get? You'll simply get f of x. Because what is the derivative of a constant? But it is going to be 0. So, which is just f of x, right? So, alright, good. So let's keep going here. Therefore, the most general antiderivative is our big f of x plus some constant term. Right, that's the most general antiderivative. So we're working backwards with our derivative rules. We look at a function and we ask, well, what do we have to take the derivative of to get that function? So let's look at a for a second. What did I have to take the derivative of to get 5? Well, the answer is quite simply 5x. Because if I take the derivative of 5x, I get 5. But it's not the most general antiderivative, right? Because that's what we're looking for, the most general antiderivative. So we have to say plus some arbitrary constant. And the arbitrary constant could be 2, it could be 3, it could be pi, it could be 1/2, it could be any number, so long as it is a constant. Because the derivative of a constant is 0. Alright, so for the next one, I want you to ask yourself, what do I have to take the derivative of to get x? And so we know that, if we take the power rule, the exponent that's up here drops by 1, right? We have an assumed exponent of 1 right there. So this is x squared, right? 2 minus 1 is 1. And now if I take the derivative of this right here, what am I going to get? I'm going to get 2x, which is not what we're looking for. So we need to multiply this guy by 1/2. So that way when I take the derivative of this whole thing, I just get x. And then don't forget to add the constant. Next one. X squared, right? Again, we're taking the antiderivative. So what do we have to take the derivative of to get x squared? Well, it's got to be one more than this number. So it's got to be x cubed. And what happens if you take the derivative of this guy? You get 3x squared. So we've got to make sure that that 3 doesn't come out. So we just have a 1/3 in front. And then, of course, don't forget to add in the constant. And if you do not add in the constant, then it is not the most general antiderivative, and your answer will be wrong. So make sure you always add the constant term. Next one, x cubed. Well, so obviously it's got to be the 4th, right? Because when you take the power rule, this exponent is going to drop by 1. And then we multiply by 1/4. And then don't forget to add the constant. Okay, now we're going up this way. So you should start to see a pattern emerging here, right? Anytime we're taking the antiderivative, when we're dealing with the power rule, that is, the exponent always goes up by 1, right? This was 2, then this became 3. This was 3, then it became 4. And then likewise, whatever number you ended up with here, you ended up with 1 over that number right there, right? 1/3, 3, and 1/2, and 2. And so this will continue. If you take the antiderivative of this guy right here, and this should say does not equal -1. When you take the antiderivative of this over here, right, so this guy goes up by 1, right? It needs to go up by 1. So we write x to the n plus 1, so following the pattern we had before. And then this becomes 1 over n plus 1, right? Because this number here and this number here have to match. And there we go. That is an antiderivative. Now let's make it the most general by adding the constant n. And so if any of these seem mysterious, I encourage you to pause the video right now and take the derivative of each of these antiderivatives to make sure that you do in fact get the original problem back. Alright, so now right here, n equals -1, right? It's the case that we could not have here. So we're going to explore that case. What does x to the over -1 equal? Well, that's simply 1 over x. And why can't we use the power rule for antiderivatives like we have for everything else? Why is this one unique in that we can't use it? Well, let's just take a look at this real fast. Let's just follow this formula we've created for ourselves. If we do that, do not write what I'm about to write down. I just want to show you where the logic fails. If you take the antiderivative here and just apply that formula, well, what is -1 plus 1? Well, we're going to have x to the 0th power. And so whatever's here must go down here in this fraction, and we get a 1 divided by 0 error. So this is undefined, so it does not work. So we got to think, okay, what can I take the derivative of and get this guy back? Well, the answer to that question, and if you don't have it figured out right now, I do encourage you to look back through your notes, pause the button, and try and figure out where this is true before saying when to write down. Pause now. Okay, here it is. The natural log of x, right? If I take the derivative of that, I will get 1 over x back. And then don't forget to make this a general antiderivative. So derivative of this will be, of natural log of x will be 1 over x. Derivative of c is simply 0 since c is a constant. Alright, what is the antiderivative of secant squared? Well, you're going to look back on all your trig rules, and what trig function do I have to take the derivative of to get secant squared? If the answer is not immediately at your fingertips, please press the pause button, find it in your notes. So the derivative of tan x is secant squared. Don't forget to make it a general antiderivative. And so make sure you do have the derivatives and for trig functions backwards and forwards, because you will need to go backwards and forwards on this upcoming exam. Alright, little f of x equals e to the x. Well, the derivative of e to the x is just e to the x. The only difference here is that we have to make it general by adding a constant in there. Okay, so all these, after going through these, should make sense. If they don't, I strongly suggest you press the pause button and review them until they do make sense. Alright, so let's go on to here. An object is traveling with an acceleration function, given here, 10t plus 1. and these are in units of meters per second per second. What is the velocity function if the initial velocity was 2 meters per second? So note that before we were typically giving a position function, and then we take the derivative of the position function to get the velocity function. And then we would take the derivative of the velocity function, and that's what gave us the acceleration function. So now we have an acceleration function, and we want to get this velocity function here. So we have to take an antiderivative because we're going, kind of up the chain, as it were. And so what do I have to take the derivative of to get this guy here? Well, that will be v of t, the antiderivative of this. We have 10 times 1/2 t squared, right? Because if you take the derivative of this guy, you'll get 10t back. And then plus t to cover this one here. And then don't forget to make it general by adding a constant. Alright. And so note this can be reduced. 10 times 1/2 is 5, and so we get this gem right here. Alright, and so now we're going to incorporate this piece right here, right? We know that this 2 meters per second is an initial velocity. That is the velocity when time equals 0. So when time is 0, we're at 2 meters per second. And so 5 times t squared is 0, plus 0, plus c. Our constant equals 2. Put it all together. The velocity function for this very specific case that fits the two pieces of information we are given is 5t squared plus t plus 2. And there we are, there we have it. That is our velocity function for this particular object. And note, this is not the kinematic equation that we might be used to working with. The kinematic equation only works when the acceleration is constant, and as you can see from this example, this acceleration is not constant. Alright, so that's it. That's the section for that. Now we move on to 5.1. And 5.1 is going to set us up to look at integrals. We're going to look at some examples that you should be very acquainted with. I just want to get you warmed up to thinking about area for just a second. So we want to find the area of the following figure. Well, we know this is the area of a triangle, and so the equation for the area of the triangle is simply base times height divided by 2. So to find the area, it's simply 2 times 4 divided by 2, so the area is 4 square meters, to be precise. Alright. And so now we've got to find the area by adding up the area of each individual triangle. Alright, because you can do that. You can break areas up. This is going to be something we're going to be doing soon. And so, you just have the area equals area 1 plus area 2, just simply broken up, right? And so for area 1, we've got a base right here of 3. And right here we've got a base of 2. Right. And note that they both have the same height, a height of 2 meters. Alright. So area 1 is, again, area of a triangle. We've got 1/2 B1, which is 3, times the height, which is 2, plus 1/2 the base, which is 2, and the height, which is also 2. Alright, so now we can go ahead and work our way through it. 1/2, 2, 1/2, and 2. And so we have area of 3 plus 2, and the area is 5 square meters. So the big takeaway of this, and I know we all know how to add areas together by triangles, I'm simply warming you up for what's to come. And so that is, keep in mind what we did. Oh, sorry, I didn't mean to do that. We broke up the area into partitions. In this case, we had partition 1, right, and then we had partition 2. This is something we're going to be using on the very back side of this handout. Alright, so for right here, we want to find the area between the curve and the x-axis. And so we're going to be using a term pretty frequently from here on out, and that's going to be the area under the curve as a term used pretty frequently. So note what we have here. We're going from here to 0, from here to 4, and note that we've got another triangle, right? So we're going to use this to find the area under the curve. That is this area I'm highlighting now. Alright, so first we ask ourselves, what is our base? How long is our base? It's 4. Then right here, what is our height? Well, our height is 2. So note that this is simply a line on our XY axis. Actually, it's a shape on our XY axis, and we're able to go right back to just regular geometry to find the area under the curve. And this area is 1/2 our base times height. And of course, the answer is 4. Okay, now here's where it gets interesting. To find the area under a general curve, we're going to be taking what we were looking at before. To find the area under a general curve, we divide the area into a series of small partitions. Right? So we broke up the bigger triangle on the front page here into 2 partitions. Now we're just going to break this area up that we're looking for into a series of small partitions, right? So we're looking for this entire area, and so the idea is that we're going to find this all by breaking it up into a series of small partitions. So let's look at one partition that we're going to make. I'm just going to make one at kind of a random spot somewhere in here. There we go. So we'll put that spot right there. We'll call this f of x star, right? Just for our special point. Right, and here's x star right there. All right, so we're going to have, a width for this guy, and this width is going to be delta x. And we're going to hold delta x constant for each partition. Now, what is the height of this guy? Well, the height is simply f of x star, right? Y equals f of x. So our height equals y of f of x star. Okay. So this is just one partition of many. So I'm going to keep that one in red. I'll draw the rest of them in a different color. So, for this guy right here, we might have the guy right there. That'd be our x star for that one. Comes through, and it'd still have a width of delta x. And so, for this one right here, right, something like that. And so it just kind of keeps going throughout the entirety of our interval. Okay. And I know it's not the most perfect drawing, but I am just trying to get the idea across. Okay. And then, I can draw the same over here. Alright, so let's go ahead and just hash this out. And so we're going to say that we've done this over here on this side. I'm just going to go ahead and just kind of draw some lines so you can kind of get the idea. Right, and so we'll say this is broken up into in partitions, right? We're going to say we have in these little shapes right here. And so first off, let's find the area of just this one little partition, and then we'll work on the rest. Okay, so we'll call this the area of our, let's call it our jth partition. Alright, and so we said that, what is the area? Well, I mean, these are all rectangles, as you notice, and so it's just the base times the height, right? The base of j times the height of j. So what is the base of j is going to be delta x. And if we keep that delta x, that width constant, we don't have to identify one for each and every one. We can just write as delta x. However, the f of hj is going to be replaced with f of xj right there. All right, so that would be the height of the function at the position xj. And so you notice that this is the method we're using. It's not perfect. There are places where it's not there's some some extra space right here. There's some other spaces where we're a little bit short, like right there. But overall it works out if you use a small delta x. We'll look at that in a demonstration in just a second. So this was only true for one small section. We want to make sure we include it for all the sections. So what we're going to do is we're going to use this symbol right here to go from the first partition all the way down to the last partition. And so this would be delta xj, which is just the same for all of them. We'll put that on the outside right here. There we go, and that's the area for everything. And so this is essentially the same thing as saying A1 plus A2, so on and so forth until you get to the last partition, right? That's what this symbol means. This is called a Riemann sum, and you're just adding a bunch of different values together. Alright, let's go ahead and look at our demonstration. Alright, so here's the demonstration I have for you guys. If you notice that I have this broken up right here into these partitions, these 5 partitions here, and I can change the number of partitions right from this here. So if we want to make it not 5, make it 6 partitions, then we got that extra one there. Notice the delta x down here. Now they all have the same width, and the shaded area, that's the area we're counting. We're adding together, and so you can kind of clearly see here, like for we've got right here, we've got some area we're not counting, but over here we have some area that we're counting that's not under the graph. So it's not a perfect one-to-one, but we can increase the effectiveness by increasing the number of partitions. So if we go to 10, it starts to get a little bit better. And as we increase it, you can see how it's starting to move in there more and more and more. All right, so notice the more partitions you have, the smaller delta x gets, and same as conversely true. And you can see right now we're up to about 60 partitions, and you can see what's happening over here. It's starting to look very much like we're really close to the area. On this side there's a lot of void space, and that just has to do with and some space added that should be added over here. So it kind of balances out the way it's set up. But note the extra area here that's not present over here. And that just has to do with the way that the function does it. It's accelerating upwards more quickly, so the void space is going to be more expected. So, Looks like we're down to 131 or up to 131 elements. Let's go ahead and bring it back down to something we can see. Back to 6. Another thing you can do is if you want to change the what's called the bounds. Change the bounds. That is, where you begin and end. You can mess with it right here. Make it a little bit longer. You can kind of see. The number of partitions is the same, but how long each partition is, the delta x of each one, is definitely longer. And so you need more partitions to really deal with this extra space. As we bring them up and kind of see how it affects it right there. Right, so I'm going to leave this for you guys to play with on the blackboard, so make sure you take a look for it. This should help you get a feel for what's going on. You can even change this function up here to anything you wish. So please play with it, see what you can, make sure you understand what's going on. Alright, so in the demonstration you saw two things on there that you didn't see on this guy. We had a B and then we had an A beginning and an end. So we want to use this to figure out, okay, what should our delta x be right there? So delta x simply is, what is the length of this guy right here? Well, that's B minus A. That's how long it is, right? The further guy minus the closer guy. And then we want to break this up into in partitions. Right, that's what we're doing. So you notice that the more partitions we have right here, the smaller this delta x. Alright, so that's the theory. Let's go ahead and do a couple of practice ones. We want to approximate the area under the curve where each square in part A is 1 unit long. Alright, so 1 unit, that's from here to here. And we have the option, let's see, the upper left corner, right? So we're picking the left corner. So that would be right here. So note the area of that is 0. And then we have this one right here. So that's our delta x is 1 unit long. The area right here is 0. Area right here, well, let's see, the width is 1, and the height, let's see what that is. Each one of these, and it's about 0.2, 0.4, 0.6, 0.8, and of course 1. And this goes a little bit above the 0.2 mark right there. So let's go ahead and call that, it's not halfway, let's call it 0.22. And so now we apply our area under the curve formula, which is the sum from I equals 1 to 2 of f of xi, or we're using j, let's go ahead and stick with that one, times our delta x, which is just 1, but we don't have to write that, and so it becomes 0 plus 1 times 0.22. So of course the answer is 0.22. Alright, that's it. That's that one. Let's go ahead and take a look at this guy here. Same graph, but now we want it to be 1/2 unit long. And so we're picking the left-hand corner. It does not have to be the left corner, by the way. It could be the middle, or it could be the right corner of the top that we could use, but we're picking to use the middle. And so we're going to go ahead and cut the partitions like so. Okay. And now we just go ahead and draw everything in. Area of 0 there. Here's this partition here. And notice that as we're drawing this, that this would in fact be an under representation of what the actual area is, right? It's just an estimate that's going through. All right, you got all this, void space here, here, and there, of course. Over here, the void space was larger, but it's becoming less so. Go ahead and take these guys out. Oops. All right, so our delta x for each of these is 1/2. Let's go ahead and put in the heights for each of these. All right, so this is 0.2. It's a little less than halfway, but I'm just going to call it at 0.05, right? Good quarter of the way. All right, next one, right here, this point there, we'll call that one 0.25. Here, let's redo that line that's kind of crooked there. Alright, so let's go ahead and call that one here. And let's see, we're at 0.55. Alright, and so, again, the width of each of these is 1/2. And so when you go to calculate the total area, it is the sum from j equals 1 to the fourth partition. And this will, and then so, of f of xj times delta x. And so it becomes this right here. And let's go ahead and fill this out. So we had 0.05 plus 0.25 plus 0.55. And note there's only 3 listed here. There was this one that had area of 0, or height of 0. Why don't we go ahead and include that just so we got everything accounted for. So note 1, 2, 3, 4, matching the 4 right there. All right. And so let's go ahead and add these up, multiply by 1/2. And so we get 0.85 divided by 2, which is and there you go. There is your answer. And so note, we're the void space that we looked at here and here, it's present here. There's more void spaces here, but the void space is getting smaller. So our estimate's getting better, and our estimated value is higher because that void space is less. So let's take a look at this next one here. Each square is 1/5 of a unit long. And so each one of those squares is 1/5. Okay, I know that one's 0 as well. Why don't we go ahead and just use the pencil so it's, hopefully we can see it a little bit better. I'd zoom in more, but that's really as close as I can get. Alright, so that's what this looks like. Note that the heights are simply taken at the left-hand corner, like so. And so again, we apply our formula, area equals the sum from j equals 1 over all these guys here. So we're going to have 5 to get to 1, 5 to get to 2, so from 1 to 10 of f of xj times delta x. What is delta x? But it is 1/5. So you're going to find the heights of each of those and then calculate them through. I'm going to leave the rest of this exercise for you as to practice individually. And I think you guys see the principles at play here, so that should not be too big of an ask. Note that this 0.425 number will be higher, but we are approaching a number as our accuracy gets better and better. Okay, so at this point I want us to ask ourselves, how could we get a true accuracy of this guy? Well, these partitions that we're working with, note that they would have to be approaching an infinite number, right? We would need that infinite number to get rid of each of these void spaces that we see right here. So what we're going to do is, you guessed it, we're going to take a limit. So we want the limit of the partitions to approach infinity, since that will give us the best estimate. So the true area will be the limit as n goes to infinity, of the sum from j equals 1 to n. We were be adding these for an infinite number of times till kingdom come. Of course, we're going to be using some techniques as we go through this. Of f of xj times delta x. I want us to think about delta x for just a second, though. What is delta x? But it is, the length from the beginning to end, the b minus a, divided by what? Divided by the number of partitions. We have an infinite number of partitions, right? And so, if we take delta x and we take the limit as n goes to infinity, what's going to happen? Well, that's going to be the limit as n goes to infinity of b minus a divided by n, right? So b minus a, that's a finite sum, and basically this becomes, some number divided by infinity. Well, that's going to be an infinitesimal, and we're going to call this infinitesimal dx, right? dx. You can kind of see where it gets its name. It's analogous to the delta x, but note that this is an infinitely small number. This is always approaching 0, but never quite getting to 0. So we can replace this delta x with a dx. Let's go ahead and rewrite this whole thing. The limit as n goes to infinity of the summation of j equals 1 to n of f of x j times dx. Okay, and there we go. That is our area under the curve. And this brings us to the next section, the definite integral. All right, and so let's recall what we had up ahead for delta x. That's b minus a divided by n. And when we're looking at the area under the curve, this is important. We have an area here that we're adding together. That's what we've been doing. But we've got this area under the curve. It's going to take on a negative value. So whenever we take the area under the curve, it's going to be this guy minus this guy. So let's look at right here. Right, this is the S, is our integral. What is an integral? An integral is the area in between the curve and the axis. Right? The area here between the curve is a positive area, the area over here is a negative area. And so we're going to use this equation right here. Now, that's the same equation we developed in the previous section. Only now we have this fancy thing as a stand-in for us, right? This simply means the area under the curve from A to B of f of x dx. Now we got f of x. Now that's the function we're finding the area, and then we have A to B here. Then we have this, dx, and so this dx, that covers this guy. It's analogous to this guy. We covered that up above, and there we are. All right, so let's take a look at what we have right here. Note this is the area of the positive region minus the area in the negative region. That's how we're going to look at this one here. And so let's say, for instance, that this had an area of 3, and let's say, for instance, this had an area of 4. Well, if you did that, then this would simply be 3 minus 4, and so your area under that scenario would be negative 1. Right, so I want to keep this general, so we go ahead and take these off, so if you're going over it, you don't mistake what's going on there. All right, so that's how that works. All right, so let's go ahead and look at some properties of this setup here. If I have the integral from a to b of f of x dx, and I simply swap the bounds, right? Instead of going from a to b, I go from b to a. And everything else is simply the same. They don't necessarily equal each other. Actually, they don't, in general, equal each other. You have a negative term right there. In fact, let me draw it in a different color so it stands out. The negative there. And so note, the a was here, now it's up there. This b was here, and now it's down there. Now let's ask ourselves, why is this the case? Well, let's think about our delta x, right? Well, let's go back to the definition that we have here. Delta x, as part of our definition here, is b minus a. So this first guy, delta x, that's b minus a divided by n. Right, of course, you're going to be applying a limit to it, but we'll ignore that for right now. And right here, delta x, well, it's not b minus a, it's a minus b over n, right? The delta x's would be flip-flop. So if you switch the bounds, you have the effect of turning this into a negative of what it would have been before. All right. Let's go ahead and take a look at this next guy. What if I take the bounds to go from a to a of f of x dx? Well, what's that going to equal? Well, what's the width going to be? 0, right? It's got no width. We're measuring the area under the curve from, starting at a, and then we're ending up at a. It's got no width. And so height times a width of 0 is going to be 0. Let's look at another one. Let's say we're taking the bounds from a to b of f of x dx. Only our f of x is a constant. Well, that's simply going to be, well, think about, the equation, or the graph of the equation. Well, the constant is going to be chugging along with a constant height the whole way through. So it's going to be the height, which is c, multiplied by this distance here, which we've already gone over, is b minus a. That's what it's going to be. Alright, and so this next one, if you take the integral from a to b of f of x plus or minus g of x, well then that's going to have the effect of just having a of b. You take the integral of the first guy, and then you plus the integral of the second guy. Same bounds. Right? It goes to each of them. And so just kind of think briefly for a moment, what would this mean? Well, we get our graph set up here. Let's say here is f of x. And I'm going to go ahead and draw g of x with, let's give it this color here. Let's say that's g of x. Well, the bound for f of x goes from here to here, right? And so the area under the curve is this guy. And then the area under g of x, well, that goes from here, and that's this guy. So we're adding the areas together. And so that's why, this area plus this area, that's what this is saying, or minus the area, if you will. So that's why you can just break them up like that. Alright, now let's say I'm taking the integral from a to b of a constant times a function of d of x. Well, I can just pull that constant out like this and have an integral that goes from a to b of f of x dx. And why can I do that? Well, what does a constant do? It's just a scaling factor. So in the original equation, what is this constant doing right here? Well, it's just being multiplied right here, right? It'd be right there. Well, all that's doing is stretching up each individual partition the same amount, so you could just bring the constant right here and it have the same effect. And so that's why we have the constant here that now is on the outside. Alright, this next one is going to prove quite useful. This is the integral from a to c of f of x dx. Alright, so let's go ahead and put the picture here. We have this function coming along here. We want to know what the total area is from a to c. And let's say we've got some point in between them, and we'll call that point B. Well, then I can go ahead and break this up to where it's from a to b of f of x dx plus the integral from b to c f of x dx. And so a big reason that this is the case, go ahead, this will be one area, this will be the other area. Well, so the area from a to b, well, that's just going to be this area right here. And then the area in blue, well, that's just going to be this area right here. If you add these two areas up, what do you get? You get the entire yellow area. So let's go ahead and wrap this up with a quick example. And so for this example, we want to know what is the integral from -1 to 1 of the absolute value of x dx. Well, so you want to break this up, right? Because what absolute value, it looks like that. The equation, if you are less than 0, is -x. If you're greater than 0, you're x. So we're going to break this up so that we go from the integral from -1 to 0, and that would be -x, because that's the definition of absolute value. It'll always be negative if you're in the 0 or less than 0, and then plus the integral from 0 to 1, now of positive x dx, right? In both instances, this is the absolute value of x, right? It would be what the absolute value of x would be doing. So we have not violated anything. And so, we're going to be looking at this area here and adding that to this area right there. So the area over here, we go out 1. It's got a height of 1. And so over here, we go out 1 and we have a height of 1. So this area right here, base times height divided by 2, that's going to be 1/2 and then 1/2. So this ends up being 1/2 plus 1/2, which is just 1. Okay. And there we go. That's it. That's all I have. Have a good day.